So now that you've watched the cute little Price is Right video, and you've watched the Boston Museum video as well as my little video just showing what we did with simulations in the classroom, we're going to look at simulations that are done by computers, which can be done in a second, versus the one in the classroom. If we'd done it, you would have seen took about 15 minutes to even just start that simulation. And then how to make decisions from these simulated sampling distributions that you see down here. So we're going to read the question first. A survey of 80 high school students was given to determine how many people were in favor of forming a new rugby team. So this is how many were surveyed. So that's our sample size. I'll write that at the top. The school will form the team if at least 25% of the students at the school want the team to be formed. Out of the 80 surveyed, 16 said they wanted the team to be formed. So this is our sample. And if we think about those little post-it notes we saw in the other video, this would be like one time you took a handful of those chips and you saw how many were peach. This is like one time I took a handful or a sample of students and saw how many wanted the team to be formed. So there's always this number that we're comparing to the chart below. So this is my sample proportion, 16 out of 20. This is what we observe. Okay, so that's 0.20. So I'm going to write observed proportion. To test the significance of the survey, a simulation was done assuming 25% of the students wanted the team, each with a sample size of 80 repeated 100 times. Create a 95% confidence interval based on the data from the simulation to the nearest hundredth, and state whether the observed proportion is within the margin of error of the simulation results. So there was a lot of information in here. First off, it says that this simulation, this information down here, is based on 25% of the students in the team. So I'm going to write 0.25 here. So think about this with that bag with the chips. Basically, if there's 25% of the peach chips in there and we took little samples of 80, so the sample size is 80. Okay, each of these little dots represents one sample of 80. So even though the actual proportion of this whole population that we're simulating this based on is 0.25, I don't get 0.25 every single time. I get values around it. So then it also tells me that this was repeated 100 times. So that means there's 100 dots. Okay, so there's 100 times that people did the sample. Now you can program a computer pretty simply. It's not too hard to do this within a second, so just, you set up some sort of loop and the program does this over and over again and creates these dots. So now what we need to do is figure out what are reasonable values that could go with this 0.25. And what we do to do that, first off here, I find the average of these dots. So if I added up all of these values together and divided by 100, right, I would get 0.249. The standard deviation, the average distance the dot is from the mean, is 0.049. So this 95% confidence interval, if you remember from the other video, 95% goes with 2 standard deviations from the mean if we assume that this graph is approximating a normal curve. It's never perfect. If we put more dots on, you would see the more dots you put on, the more it approaches what a normal curve is, but we're going to use that idea that it's close enough that we're going to use 2 standard deviations. So what I do is I start with my mean, 0.249, and I add or subtract 2 standard deviations. So I'm going to put this in a different color. I should have put this in the front. 2 standard deviations. So we're going to go out 2 standard deviations, hoping that we get 95% of the data. So I'm going to move this up just a little bit. So if I calculate this, if I subtract the 0.049 or minus 2 times 0.049, I get 0.151. then if I add it, I get 0.347. So now I'm going to round to the nearest hundredth. So I get 0.15 to 0.35 if I do the rounding, and that's the answer that's going to go in here. So the confidence interval based on the simulation is 0.15 to 0.35. So the observed proportion in the sample survey, so my observed proportion, if I move back up the page, remember that was this number? That's what happened when they did the survey. So that observed proportion of 0.2 or 0.20, whatever you want to use there is fine. That 0.2, and we're going to mark this on the graph, is inside of the confidence interval, which is here to here. So we're going to say, if you click on this, this says it's within the margin of error. And basically the margin of error is just really closely related to the confidence interval. If you just know it's within the confidence interval, that kind of means the same thing, but technically the margin of error is just how much you went out to the sides. Okay, so what this means is that even though the answer they got from their survey is 0.2, that could have come from a sample with a proportion of 0.25. So this, I tried to really explain what's going on, and this is how you make statistical decisions, because if you don't survey the whole population, you really don't know about the whole population. You have to say, well, that's reasonable. It's reasonable that that could be the population proportion if that's a sample that came from it. So on the next page, I'm really going to focus on what you need to do to solve the problems. On this page, I kind of tried to explain, what's the whole process. So this problem is about coin flips. It says Olivia flipped a coin 40 times and 12 of the 40 flips were tails. She wanted to see how likely a result of 12 tails and 40 flips would be with a fair coin. So a fair coin means a 50-50 coin. So first off, our observed proportion what happened when she did this one time, her one sample, is 12 out of 40. And if I type that in my calculator, that comes out as 0.3. So the question is 0.3, and that's like the most awful 0.3 I've ever seen. Sorry about that. Is 0.3 something that could reasonably happen with 40 flips of a coin if the coin was fair? Okay, so really, in an ideal world, if the coin is fair, I would get exactly 50% of my coin flips were heads and 50% were tails. We know the world isn't always perfect, right? If you flip a coin, sometimes it's not going to come out to 0.5 exactly. So we're going to see, is this too far away from that 0.5 to be reasonable? Maybe the coin is not fair, or is it within that margin of error, within that confidence interval? So here it says, so Olivia used a computer simulation to see the proportion of tails and 40 flips repeated 200 times. So each of these dots is 40 flips. And there are 200 dots here. So we're going to create our 95% confidence interval. Okay, so remember that's just mean plus or minus 2 standard deviations. So we see the mean, right? The average of all these dots is pretty close to that 0.50 that we're expecting, plus or minus 2 times 0.08. So if I type that in my calculator, right, 0.497 minus 2 times 0.08 and then plus 2 times 0.08, I get 0.34 to 0.66, rounding to the nearest hundredth, right, which is what the directions say. So in this situation, if you were to do 40 coin flips and your coin was fair, you would expect that proportion to come in between 0.34 and 0.66 95% of the time. That's what this 95% confidence interval is. So it's possible you could get something outside of that, but these are the common, remember how we said most values are within 2 standard deviations? This is the central value, the central area that we're going to say these are the reasonable ones. So the confidence interval based on the simulation is 0.34 to 0.66. So the observed proportion of tails, which was 0.3, is not within the margin of error. Okay. So what that means is basically this person, Olivia, when she got the 0.3, it means her coin might not be fair. Okay. We don't really think it's likely it could be fair if it was inside this confidence interval, but it's outside. So we could say that it's likely not fair. We can never be 100% sure of anything with statistics because it's possible that you could get crazy lucky and get like heads, 40 times in a row. That is possible. Okay. But it's not within that probable confidence interval of things that happen with a fair coin.